Welcome to my presentation on the kinetic theory of gases. My name is Bernard Taylor, and this is Fez Physics. Why Fez Physics? Because I am a physicist. Get it? Well, let's move on. You've hopefully looked already at the gas laws, and we've got Boyle's law over here, where PV is a constant at a constant mass of gas, at a constant temperature. Charles' law, volume over temperature is a constant. And the pressure law, P over T, is a constant. We can combine these three laws and we get that PV over T is a constant. That leads to, well, what some people call P1 V1 over T1 equals P2 V2 over T2. I've expressed the same equation slightly differently. If we've got 1 mole of gas under these conditions, standard temperature and pressure, that leads to P0 V0 equals NK T0. And that leads on to here and gives us a value for the Boltzmann constant. Well, I just mentioned that. Of course, the Boltzmann constant is given in your data booklet anyway. I would stress that N, remember N, big N, is the number of molecules, and small k is the Boltzmann constant. Up at the top over here, we've got a relationship which those of you who do A-level chemistry will be more familiar with. We're not going to touch that equation in what follows. So the gas laws will be combined. PV over T is a constant. PV equals NKT, and this is for an ideal gas. Now, the kinetic theory of gases was developed by James Clerk Maxwell and Ludwig Boltzmann, and they're quite complex mathematical models based on certain assumptions. These models assume a simplified, idealized version of a gas and do get very statistical, but we're going to do away with all that complex statistics. So let's just read through these assumptions. That we have large numbers of particles present in a gas. The particles collide frequently with each other and with the walls of their container. The time of collision is small compared with the time between collisions. The particles are moving randomly in all directions with a random range of speeds. The volume of the particles themselves is negligible compared with the volume of the container. Collisions between gas particles and the walls of the container are perfectly elastic. We'll come back to this point in a moment. And the forces between the particles are negligible. Now, it may well be that you're asked in an exam question to say, or just to mention, some of the assumptions of the kinetic theory of gases. Be prepared to mention 2 or 3 of them, perhaps. And I've highlighted in red the last 3, and I think they're easy ones to mention in an exam. So, learn them. Now, let's suppose we have one particle in a particular volume. This shaded side has an area A. The molecule is traveling a distance A. It will hit this side, bounce back, travel again, and hit this side again. Now, for each impact, the change in momentum, well, mv is the final momentum. So going in that direction is positive. Going in this direction is negative. So it's the final momentum minus the initial momentum, which is 2mv. The molecule has a speed v, and in a time t, it'll travel a distance v times t. To make one collision, it would have to travel a distance 2a, sort of there and back from the shaded side. So in a time t, it'll make vt divided by 2a collisions. So the total change in momentum in a time t at the shaded end is 2mv, times Vt over 2a. And if we work that out, that gives us mv squared t over a. Right, we know that impulse is force times time, which is change in momentum. So force times time equals mv squared t over a. T cancels and we're left with F, force, on the shaded end equals mv squared over a. Now, let's go a little bit further. If we've got n molecules in the box, each of mass m, moving at the same speed v, but in all directions, how many on average are moving left, right, right, left in that particular plane? Yeah, it's going to be a third, because another third will be moving in a plane vertically, and another third will be moving in a plane in and out from where we look at the picture of the box. So what is the total force on the shaded area? Yeah, it's going to be a third. F equals a third nmv squared over a. And what's the average pressure on the shaded area? Pressure equals, yeah, pressure equals force over area. So that pressure P equals 1/3 nm v squared over, now we've got the little a coming over here, but this big A is the area of that shaded side. And what is little a times big A? Yes, that's right, it's the volume. So let's say P, the pressure, equals 1/3 nm v squared over v. Now be careful, this is small v, which is the speed squared, and big V is the volume. Okay, moving on. So I've repeated my equation at the top, and I'm allowed to repeat myself. I'm a teacher. Don't teachers do that all the time? Our model of a particle in a box is much too simple. We're going to have n particles in a gas, but the particles won't be moving directly along the three axes that I indicated, and they certainly won't be moving at the same speed. So let's assume that the particles have a range of speeds and are moving in random directions. Yes, we could resolve each speed along each of the three axes and determine an average value for the speed, and your textbook probably does that. But you won't be asked to do that in an exam. So let's suppose we've done this, and let's, instead of v squared, write c squared, enclosed by these brackets. So PV equals 1/3 nm c squared. And all these brackets mean is that it's a kind of average value, a mean value. So it's the mean square speed of all the gas particles. Now, of course, you're usually given this equation in an exam, so don't worry too much about the derivation, although there are some very relevant points that could be brought up or developed in another type of exam question, particularly points about the change in momentum. So the root mean square speed of gas molecules, the RMS speed, is the square root of the mean square speed. Now, that's how it works. Let's see what that means with a real example. Let's suppose we have 5 molecules with these speeds. The mean square speed, that's this, equals each one squared divided by 5, because there are 5 molecules in this case. That leads to the RMS speed, which is the square root of what we get, which is about 308 meters per second in this case. Now, we've already said that PV equals NKT. We've established that PV equals 1/3 nm c squared, and I've defined my terms. It's interesting, isn't it, that n times m is the total mass of the gas, and that really we've got a microscopic property which relates to some of these macroscopic properties of a gas. And for me, this is part of the beauty of the way the kinetic theory of gases relates to the gas laws. Anyway, equation 1, look at it, PV is a constant at a constant temperature. In equation 2, PV is also a constant at a constant temperature. At a constant temperature, c squared is going to be a constant. So, hey, this is Boyle's law. Now, equation 2, PV equals 1/3 nmc squared. Now, what is n times m? That's the total mass of the gas. Bring the v to the other side, we've got the volume, so we've got mass over volume. Oh, isn't that density? So, putting the symbol in, rho, with a sort of P with a curly tail, that's the symbol that we often use for the density of the gas. So pressure equals 1/3 rho c squared. Moving on. I've got my two equations here again, and of course both of them have PV, so let's put one equal to the other. That's what I'm doing here. I'm cancelling n, bringing the 3 over to the other side, and I've got mc squared equals 3 kT. Oh, let's put a half in. Oh, why a half? Kinetic energy. So a half mc squared equals 3 over 2 kT. And of course, this is the mean or the average kinetic energy of a molecule, a single molecule. And notice that this term is proportional to the temperature. Let's, in a sense, go backwards. That's for one molecule. We've got n, big N molecule, number of molecules in a gas. So this term, multiplying both sides by n, this term becomes the total kinetic energy of a gas. And in an ideal gas, the particles only have kinetic energy and no potential energy. There are no forces acting. There are no, what I sometimes describe as springy bonds involved in molecules, which if we have an oscillating diatomic molecule, we're talking about vibration of the molecules. Let's forget about all that. So in an ideal gas, the particles only have kinetic energy and no potential energy. So the total energy of a gas, we've already established, is 3 nkt over 2. That's the total kinetic energy of a gas. So that's the internal energy of a gas. And if we have a temperature increase, then the energy will increase by a corresponding amount given by this equation. It's a useful relationship to bear in mind for exam questions. So let's move on. Now let's look at this distribution. In particular, let's just look at the distribution for low temperature. On the y-axis, we've got the number of particles with the speed u, and along the x-axis, we've got the speed u. At the two ends of the distribution, well, only a few particles have small speeds, and only a few have large speeds. Let's remember that, and please just be aware of how this distribution changes as we go to a high temperature. The peak shifts to the right and the peak is depressed. I'm not going to go into that in too much detail at the moment, but remember this. Now, we've got a few exam style questions. in question 1, the term c squared represents what? Well, don't we know that already? Is it the root mean square value? No, certainly not. It's the mean square speed of the molecules. So that is answer C. Now look at question 2. We've got a volume, we've got a pressure, we've got the number of atoms, we've got the mass of a helium atom, and we're asked to calculate the root mean square speed. PV? PV equals 1/3 nm c squared. So rearranging that, we can get c squared, and we can put in the numbers, and that will give us a value for c squared, and from that we can get the square root. And the square root, 1.2 times 10 to the 3 meters per second. This value may seem a bit large to you, but it's fairly normal with the root mean square speed of atoms in a gas. Okay, question 3. The average kinetic energy of the molecules in a gas is proportional to, oh, could it be C? Well, whether we've got the mean kinetic energy of a single molecule, we said that was equal to 3 kT, so it's certainly proportional to T. If we've got all the atoms in a gas, we're just multiplying both sides by big N, and in that case, it's also proportional to T. So the answer is C. It's quite a common question, so be prepared to bring to mind that relationship. Okay, when the absolute temperature of an ideal gas is doubled, the internal energy of the gas changes by a factor of, well, the ideal gas has no potential energy. All the internal energy is kinetic energy. So if the temperature is doubled, the kinetic energy and hence the internal energy is doubled, and the answer is C. Okay, a sealed gas jar contains a mixture of different gases at a given temperature. The mean kinetic energy of the molecules of each gas, blah, blah, blah. At a given temperature, kinetic energy. Well, for each molecule, the kinetic energy is a half mc squared, which is 3/2 kT. So it's going to be the same for each gas in the mixture, because whether we've got one molecule with a mass m or another molecule with a slightly different mass m, that is still going to be it's going to be the same for each gas because it's dependent on the temperature. So the answer there is D. Okay, how do air molecules, the movement of air molecules, how does that explain the pressure of a gas, the pressure on the ground? Well, hey, the idea here is very simple. Molecules bounce off the ground, and each bounce transfers momentum to the ground. Okay, the force on the ground is equal to the rate of change of momentum. Remember, impulse equals force times time, which equals change in momentum. So the force is the change in momentum over time, which is the rate of change of momentum. And then pressure equals force over area. Now, if I was you, I would remember those 3 points, but I would put in the equations. Force times time, impulse is force times time, which equals change in momentum, and force equals change in momentum over time, delta mv over t, or delta mv over delta t, perhaps more correctly. Okay, I've got an equation here, PV equals 1/3 nm c squared. Well, this term here also is this, it's another way of writing c squared, the mean square speed. Okay, by assuming the air at 20 degrees C is an ideal gas, show that the root mean square speed is about 500 meters per second. We're given the mass of a molecule, we're given the Boltzmann constant, and I've reminded you that PV equals NKT, but I'm sure you didn't need any reminding. So, PV equals 1/3 nmc squared, which is NKT. So C squared is 3kT over m. Temperature, we need to be working in Kelvin. So I've done the conversion for you, 293 Kelvin. So C squared, putting everything in, works out to be 2.62 times 10 to the 5, get the square root of that, and it's about 512, let's call it 510 meters per second, not having too many significant figures, which is close to our 500 meters per second. Good. Now, remember this value for the mass here, and let's look at the next part of this question. We've got a value for atmospheric pressure. Estimate the rate at which air molecules collide with an object of surface area 0.56 square meters to provide this pressure. And we're asked to state one assumption. Well, pressure equals force over area. I'm always telling my students to draw little diagrams to help them visualize what's happening. Force equals pressure times area. So force equals the pressure that we're given times the area, which is 5.6 times 10 to the 4 newtons. Now, let's just think about this, the rate at which air molecules collide. This force is from n, small n, collisions per second, let us suppose. So the change of momentum of one molecule is 2 mv, and that will be 2 times the mass, that's the mass of a molecule. I told you to remember that on my previous slide. We've worked out V. So with n collisions per second, the rate of change of momentum is this times that times n. That's all. Now, that force is the rate of change of momentum. Now, we know what that force is, and that equals, yes, this value, which is the rate of change of momentum. So we can use this equation here, and we can quickly work out what n is, and that's a pretty large number of collisions per second. Assumptions, well, all collisions are perfectly elastic, and we're also assuming that molecules hit the surface at right angles. They all won't hit the surface at right angles. Some will hit it at rather more glancing angles. And another assumption could be that all molecules are moving at the RMS speed. Now, as we come to the end here, I would like you to find out a little bit more about Brownian motion. And you'll find that Brownian motion has something to do with Einstein. You could find a good YouTube video about Brownian motion and watch that. So, thank you very much. That's Fez Physics. Stay tuned. Thank you very much and keep working.